And we're live. All right. Hello, everyone listening to the recording. This is the 13th session of the Compute Over Data Working Group, and happy Valentine's Day. We've got a pretty packed session today. We've got Daniel from Nexus.xyz, who's going to tell us about the new project that they're launching. Very exciting stuff. And we also have John Fletcher, who's joining us all the way from Cambridge crypto team. And if we're lucky and we get through broadband issues across the Atlantic undersea cables, we'll have him on today. If not, we'll stitch him in on a future session and add it into the YouTube playlist. So with that, Daniel, if you're ready, I'll hand it over to you and you can start sharing and lead us to whatever content you like.
All right, amazing. Thank you, Wes. Can you all see my screen?
Looks good.
Yeah, looks good. Okay, amazing. Yeah, thanks a lot. Hello, everyone. As Wes said, I'm Daniel. I'm the founder of Nexus Labs. That's the official company name. Nexus Labs is a company that we're working on verifiable cloud computing in a decentralized manner. I believe I'm very excited to talk to this group because we're all doing stuff around decentralized computation. And that's exactly what we're doing, decentralized verifiable computation. And so some background about us. Nexus Labs was originated at Stanford. And in fact, we're based here at Stanford, like right outside campus. In fact, I'm right now outside campus and I can see it through the window. So we started through the Applied Cryptography Lab, as part of research into verifiable computing and blockchain in general. And, the company also went through the Stanford Blockchain Accelerator. And just in general, our roots are very over there at the university. And so the problem we are trying to solve here is, we're just attempting to scale all kinds of blockchain computation, whether that's by giving them, hidden capabilities around computation, storage, and I/O. And I will explain a little bit what we mean by I/O. But, the classic scalability problem, which, for instance, on Ethereum is addressed by rollups, we're providing kind of like a different way to achieve scalability that is way different, very different than rollups, very different than everything. And it's through a kind of form of off-chain compute using verifiable computing, such that, we run things off-chain and just verify them on-chain. So the solution, as I mentioned, is, how can you achieve verifiable computing such that you can verify that, some set of people run a computation correctly off-chain or are storing your data, as the folks from Filecoin are very aware of, or, that you have I/O capabilities. And by I/O capabilities, we mean, how do you make, let's say, for example, a blockchain interact with another blockchain, a rollup, the internet in a way that is verifiable and secure, such that that the interaction between any two decentralized systems is computationally correct. So, computation, storage, and I/O. And on that note, let me say something. Maybe you're familiar with a little bit of the classic theoretical computer science, and part of theoretical computer science and the classic computer architecture is this notion of a von Neumann architecture, of a von Neumann general purpose machine. And a von Neumann machine is a machine that has access to computation through like the CPU, storage, and has input and output access. So something that we are building, and then we'll talk a little bit more about this, is kind of like a general purpose von Neumann decentralized verifiable machine. A little bit of too many words, but I will explain what all of this means. So at Nexus Labs, we're building two projects. One of them is called Nexus. And the other one is called Nexus Zero. We still don't have a logo for that, so excuse us there. So Nexus is essentially a network of networks that is trying to achieve verifiable computing through multi-party computation and replication. So for instance, we just run any program that you want, specified as a WebAssembly binary on a decentralized network, which replicates computation through a proof-of-stake decentralized computer network that is allocated specifically for you. So it is in a form like a blockchain. With the difference that these blockchains, number one, are application specific. And number two, are connected to Ethereum directly. Oh, and number three, they're serverless. They're kind of like a form of serverless computing. I will explain more about that later. Secondly, Nexus Zero is the zero knowledge counterpart of Nexus, which is attempting to achieve verifiable general purpose compute through zero knowledge proofs and a zero knowledge virtual machine we're building. And well, the difference is, whereas Nexus achieves verifiability of some degree through multi-party computation and state machine replication, Nexus Zero achieves it simply through zero knowledge proofs and proving whatever program you upload to your network. And in fact, both of these networks, kind of like complement each other very well. But I will talk a little bit more about that later. So, well, this is how Nexus looks like. Nexus is literally a network of networks, all of which belong to the same kind of like proof of stake network. And essentially, you as a developer, what you do is you deploy your application to one of these networks. Like, here in the diagram, we have seven networks. So your application goes into one of them, and you specify how many nodes you want your application to be run on. And so your application runs on one of these networks, which you rent, similarly to AWS or Google Cloud. We're literally attempting to achieve the same experience as AWS Lambda in that regard. So you upload your program, it runs on a dedicated computer network. This computer network is connected to the Ethereum blockchain, at least for now. And well, it's able to run arbitrary computations, including storage, like storing images, also achieving I/O. Examples of I/O is communicating with the internet, communicating with other Ethereum smart contracts or rollups, including accessing historical state, just achieving general purpose computation over any kinds of data. So essentially, our thesis here is you have a blockchain, let's say Ethereum or an L2, and if you need enhanced computational capabilities that are not achievable within your blockchain environment, perhaps because you cannot do floating point arithmetic, or you cannot exceed the block guess limit, or it's just simply a very constrained computational environment, then perhaps you can resort to cloud computing, verifiable cloud computing network that computes your program or part of your program off chain and injects the results of the computation back to your smart contract. So for those who are a little bit more aware of kind of like the distributed system side of things, you might notice that when multiple parties compute something together, theoretically the upper bound on the allowed number of malicious parties that collude is around 1/3 of the nodes. So if you're a blockchain smart contract user that wishes to offload computation to Nexus, essentially what you're making implicitly to achieve higher computational power and storage, etc., it's a trade-off in terms of security. because now you're not running everything on the underlying blockchain security mechanism, but you're outsourcing part of the computation and therefore conceding a little bit on the side of security. And now you're trusting something like a Nexus cloud. But well, regardless, that's how it works. It's kind of like a serverless cloud computing platform that is directly connected to Ethereum. And what this enables is what we call decentralized cloud functions, which are literally just like AWS Lambda, but running on a decentralized network, engaging in, proof of stake consensus and, participating through protocols like doing multi-party computation. And when we talk about multi-party computation, what we mean is things like threshold signatures and distributed key generation that allow the networks to synchronize together and submit joint transactions to blockchains. So that's what Nexus does. And an example of how Nexus looks like is, well, you write your program, which is, you can write them in Rust, C++, Go, anything that compiles a WebAssembly. Here, I'm showing an example of a cloud function. So you declare your function and, just write the code that your function will do. And it's just like a normal program that you would traditionally upload to AWS. But instead of uploading it to AWS, you upload it to Nexus. And on Nexus, your program runs equally well. In addition to that, your program has read-write access to Ethereum state. So that's literally how it works. And now I'm just going to pause a little bit because we're now going to jump out from Nexus and into our newest project we recently announced a few days ago. We're still building both in development. We're actually close to opening Nexus to something like a DevNet. But we're building Nexus Zero, which is, as I mentioned before, kind of like the zero knowledge counterpart of what Nexus is trying to achieve. And so while Nexus achieves verifiability through multi-party computation, Nexus Zero achieves verifiability through zero knowledge proofs. And well, the mechanics are very similar. Nexus Zero is like an AWS Lambda, in which you essentially upload a program to a permissionless network of provers. This is also a Rust program, and we generate a proof for the computation. And these proofs get submitted back to Ethereum or any other smart contract system that supports our cryptographic primitives. And so this essentially enables a way to outsource computation from smart contracts to a decentralized network of zero knowledge provers. This is kind of like the architecture of the network, but it's simply that. You have a smart contract. You say, I want to upload this computation to Nexus Zero, and Nexus Zero just computes this for you. It generates a proof, and then it submits it back to Ethereum where it gets verified. And so something important is that using Nexus Zero, well, the computation is provably secure, number one, and number two, it does inherit Ethereum security instead of depending on others' assumption, as it is with Nexus. And so for Nexus Zero, we're building a zero knowledge virtual machine that is not a CK EVM, but it's just a CK VM designed for the RISC-V architecture and operating. It has the von Neumann architecture that I previously described, which means that among other things, that it works essentially as a general purpose computer. So it is designed to run traditional programs just like Nexus, but like Rust, C++, and Go. And how it works is we have a universal CK snark circuit, such that we have this little diagram here, but the important part is that the prover receives an encoding of the program as part of the input, and so does the verifier. And so using a single circuit, which is a universal circuit because it accepts any other program as input, we're able to verify any general purpose computation, and specifically those written in Rust, C++, and Go. And so, the analogy with Nexus is, with Nexus 0, you can achieve almost the same. So you also can write applications in Rust, just as the one that I'm showing here, which is just a normal Rust application, using traditional languages. You compile it into our representation for Nexus 0, and you upload it to Nexus 0, which, as I mentioned, is a permissionless prover network. Nodes on Nexus 0 simply compute the proof for your application, which then gets submitted back to Ethereum, and that way you achieved verifiable computing that was outsourced from Ethereum into your smart contract. So same thing as Nexus, except that probably verifiable, but it of course has a set of trade-offs that Nexus and Nexus 0 differ on, but we can leave that for some other time. So just finishing our talk, we're very well capitalized, we're venture backed, by great partners. And we are accepting a small number of early partners to try out our technology, especially smart contract developers that wish to, achieve crazy computational stuff. Just shoot us an email and follow us on Twitter. We recently made an announcement over there too. Our handle is down there. And we're very actively hiring. We're hiring mostly senior scientists, cryptographers, and anyone that is interested in zero knowledge proofs, feel free to contact me or the team over there. And that's all. That's all. Thank you very much. Thanks, everyone.
Fantastic. Thank you, Daniel. This is tremendous. I love the vision. I love the investment in the core underlying cryptography that you guys are making, which benefits the entire community.
Thank you.
I'll give everybody else an opportunity to add questions in, but I would love to just hear one quick question for you is your opinion about the use cases that might be underserved with the current infrastructure, which is predominantly smart contracts and then AWS, Google Cloud. Are there any use cases or problems to be solved that you think could both benefit from the tech you guys are building?
Yes, quite a lot. So number one is, for example, accessing historical blockchain state, right? So if you have a smart contract, you want to access the state of your blockchain, maybe a year ago, you can't do that. So the only way to do that is you set up an AWS web server and you do everything that you would do. But the difference is that it would be centralized. By deploying it on Nexus, it becomes decentralized. And so you can build a whole protocol that remains decentralized and has this computational capabilities. So that's one, accessing historical blockchain state. The second one is making your smart contract event driven. So if you connect your smart contract to one of our cloud networks, you can specify in your cloud network application that it should execute the transaction on Ethereum every time an event happens on this other smart contract or on this other Ethereum-like network. And so that achieves quite a good amount of what you would call interoperability or synchronization, state synchronization between different applications. So particularly excited about that. And lastly, just the fact that there's a lot, anyone who has coded a smart contract knows that you cannot do floating point arithmetic happily and easily, right? And so if you are trying to do stuff like matrix multiplications, solving equations or whatever thing that uses floating point arithmetic, if you need a lot of power, you can just run it on Nexus, receive the result back on your smart contract, and that would be it. I have some ideas of which applications could use floating point arithmetic, but the examples are just so wide. I think it's clear that there's a lot of you can do with floating points. So I'm particularly excited about that too.
Brilliant.
Yeah, happy to take any other questions, guys.
Hey, Daniel, this is Michael, and actually a wonderful presentation. And just one thing I'm curious as you're going through the slides, right? I wonder, like in a serverless structure like yours, how do you orchestrate the incoming tasks?
Oh, yeah, that's an excellent question. And in fact, I think that's exactly where we're innovating as opposed to, the academics and all that kind of stuff, because orchestration is, I believe, something that hasn't been explored on a decentralized network of networks. And so how it works is there are two ways. So number one, if any of you are familiar with the internet computer, for example, the way they achieve orchestration between networks is by setting up another network, like literally another network that is just designed to run an application that orchestrates. And orchestration is happens through a market making application. So literally the orchestrator is another network that orchestrates the rest. However, that has a downside. And the downside is that if the orchestrator is, compromised, then the whole network is compromised. And so we're not taking that approach. In our approach, the orchestrator is actually the whole Nexus network. So the whole Nexus network, meaning the whole network of networks, operates as the orchestrator and does the matchmaking mechanism, which is just like market making. It receives bids and requests, and it just ranks them, and it distributes jobs. But everybody is engaged in the computation of that orchestration mechanism, which means that the network doesn't have this security vulnerability as this other design did. Number one. And number two, how it operates is every node then is essentially running two different tasks. Is running tasks for consensus on the whole Nexus network, which includes this orchestration mechanism, etc. And it's running its particular task for its own application that the user uploaded. So it's kind of like running two processes at the same time. Consensus for its own application-specific network and consensus for the whole Nexus network. And that's it. That's how it happens.
I see. So which route are you picking for Nexus?
No, it's the second one. It's the second one, not the first one, because the first one.
I see.
Yeah. The first one, it's more efficient by far, but it does not achieve great security because of what I just described. In our case, we're more conservative. We're more worried about security than probably everything. And so we're taking the second approach. Yeah.
I see. And also I see, as you mentioned, you're leveraging WASM. So I guess besides the, being portable and language agnostic for developers, it's you're also looking to have a greater speed, right? So it boosts up very fast, right? But in a decentralized setting, whenever a worker is called upon, right, it boosts up this runtime or VM, and now it's retrieving tasks, right? It's downloading the files. And so in this process, this becomes kind of uncontrollable, right? You don't really know, how long this part will take. So how do you reconcile the fact that, okay, we want this to be awesome, we want this to be really fast, but also in a decentralized setting, we don't know, there's no hot functions or cold functions per se. So how do you deal with this?
Yes, exactly. So no, and actually I'm very excited to talk about that. So for WebAssembly, you can define arbitrary host functions that get injected into the runtime. And how it operates is So Nexus has this Nexus virtual machine, which is the one that, the WebAssembly runtime in which applications run on. And the Nexus virtual machine injects host functions into the WebAssembly runtime, which user applications can just call on. And so when that call happens, essentially, the runtime gives the computation back to the node, and the node can just do anything it wants. So for instance, let's say that your Nexus application says, go and read the state on this on Ethereum, or maybe you go and fetch this data from the internet. In the case of the internet, for instance, you can just simply have like a timeout. If the request does not resolve within this time, then we block it. You also have to achieve consensus on what the internet said, which is a different discussion in and of itself. But for example, with Ethereum, when you query the Ethereum blockchain, you also have to have some sort of timeout, unless you're running Ethereum natively as a light client. So, all this kind of like questions about how do you, especially because I think this is what you're trying to get to, is how do you keep your applications deterministic and gas metered if you're running applications on a WebAssembly environment that is calling into non-deterministic, non-gas metered host functions. And the way is simply the node handles that, and is part of the consensus protocol to, for example, limit the time this host functions might take on the node, and how many calls should you make, etc. So it is made deterministic by the node, and so if you have deterministic gas metered host functions combined with a deterministic and gas metered WebAssembly runtime environment, then everything is deterministic. And if everything is deterministic, you can reach consensus. And if you can reach consensus, you're happy. Because if you can't reach consensus, then, well, you're destroyed. So maybe that kind of answered your question, but let me know if that's not the case.
I see. So I guess like one thing I'm trying to get at is say if I'm running a node for Nexus, right? Am I required to basically download all the possible functions that will be called?
All the posts. Oh, I see. No.
No. Okay.
So yeah, exactly. Yeah. So that's part of the I think I got a little bit confused about what you meant by functions.
Yeah, sorry.
You mean applications, right? User applications. Yes. So no, you don't need to download that. You don't even need to download the state of any other application except the one that it has been assigned to you. And even when you are unassigned to that application and reassigned to some other, you can completely delete the state and storage of the original application that you were running and run the new one. So every network is just application specific. It does not know anything about the other applications, except perhaps like the hash of the function or something like that. And that's it. So you don't. It's literally kind of like renting AWS servers to some degree.
I see. So if I want to deploy something, I would say, hey, Nexus, I want 10 machines and I want them for say the next 24 hours.
Yeah, exactly.
I see. So it's priced by time.
No, it's priced by execution. So how it happens is you rent it, but it is on a gas meter way. So you have like a tank with a balance, and you have some amount of money there. And every time your application executes, which is in response to events like Ethereum events or internet events, it consumes a little bit of your gas tank until it hits zero. And so all you have to do is ensure that your gas balance is always positive, so your application can keep executing.
I see. Thank you.
Yeah, of course.
Fantastic. Well, clearly, I think Daniel, you've hit on a nerve within. Folks are very interested in your technology, so I don't want to stifle the questions, but I will, if you don't mind, route the folks to our Slack channel to ask you further follow-up questions.
Absolutely.
I think you guys are in the middle of a lot of things. ZK, unstoppable applications that a lot of people care about. So thank you for all the content you shared.
Yeah, thanks a lot, Wes. Yeah, and everyone feel free to ping me anytime. I'm more than happy to discuss any of this.
Very good. All right.
A strategy for decentralized science. And yeah, if we can skip to the next slide.
Okay.
I just want to quickly tell you about this is our founding team. Ying is online actually, so you might be able to help you guys with any questions. I'm the CEO. Philip David at the end is he was 20 years at ARM for as general counsel, ARM Holdings in Cambridge. So he's been a big inspiration, particularly as I'll mention, we're interested in open source and the economic model around that. So he's he did a lot of stuff with open source while at ARM Holdings. So that's just why I wanted to flag that one up. Okay, we can go to the next. So what we're interested in more specifically is this notion of open and collaborative, which is something that we came up with. I mean, there may be an equivalent notion out there. It's a pretty simple thing. It's defined with these 3 points that anyone can submit a contribution. And we're thinking about something like a software project here, of course, like a collaborative software project. Full disclosure of methods and results. Resulting knowledge is a public good. And if you are familiar with open source, you probably realize that these open source meets these criteria. Also, interestingly, science, or at least academic science, meets these criteria too, or at least it should. People are supposed to disclose their results, and the scientific knowledge which is produced is a public good, assuming it's not patented. Which things like early stage applied and fundamental science, which is typically government funded, fits that bill. And the interesting thing about this, you probably won't find it too controversial, but you can dig into it if you like, is that open and collaborative projects, when you have a complex project, if it's open and collaborative by this definition, usually has a lot of benefits. I mean, one reason is that people can sort of check each other's work, provide feedback, peer review. If somebody stops working on it for some unforeseen reason, then other people will carry on because they know that they'll get the benefit of the project. So this is really just the reason why open source works. It's kind of a very useful thing. You can crowdsource expertise, and people can spot interesting kind of spot problems earlier, and it tends to just result in a better quality, high quality product. So, but this is all predicated on there being sufficient participation in the project. And you probably know, there were very many famous open source projects, for example. You don't really hear about the ones that aren't famous. They don't get very much participation. But things like Linux, when it works well and you get lots of people chipping in, you can be extremely successful, and it just ends up with a better product, produced more quickly and at lower costs. So it has all these fantastic benefits. So if you can do a complex project and make it open and collaborative, that's great. But the interesting things are that it's sort of economic in some circumstances and not so economic in others. So we can skip to the next one. So as I said, we're kind of inspired by open source software. You all know what open source software is, actually, so we can skip on to the next one. And in this case, that they produced this code which ends up being a public good, and people chip in, and some people work part-time for free and so on. And it's altogether a fantastic thing. But there are some kind of criteria for open source projects which work better than others. As I said, you don't really hear about the ones that don't work so well. You can open source anything, of course, but it doesn't mean to say it's going to be a successful project. So the successful ones tend to be that the outcomes, such that the outcomes are uncertain but not too uncertain. I'll come back to that one in a second. The code base is large. The reason why that's relevant is because open source licenses lean on copyright quite hard, and if you can just the code base is quite short, you could re-implement it and circumvent copyright, and then you have a problem with a free rider. Number three, code base is highly modular. This means that lots of people can chip in their part-time, and it means perhaps 100 part-time people would be more or less equivalent to 10 full-time people. So it sort of scales in that interesting way, and it means that even though open source, the model doesn't typically offer payment to contributors, because people can afford to participate in their spare time, and they're hoping to get a better piece of software out of it, then the projects can gather momentum for that reason. So the sort of interesting structure, the architecture of certain projects work better for open source than others. Going back to number one, outcomes are uncertain. That really just means that every complex project, the outcomes are uncertain. So there's making it open and collaborative means that, you know, for uncertain projects, you tend to get a better outcome, you know, sort of more efficient. But if it's too uncertain, you know, we'd be thinking about some kind of open source project to, I don't know, stabilize a plasma for a fusion reactor, or, you know, are we some kind of exotic piece of fundamental research. The incentives to participate are generally reduced, because you don't really know that you're going to get a usable, a sort of useful piece of software out of it. And one of the reasons why people contribute to open source software projects is because they want to have a better piece of software that they can actually use. So if it's some kind of experimental type of software using some extremely sort of esoteric stuff, which may not pan out, you know, in the next 20 years, and then the incentive is reduced. Okay, we can skip to the next one. So this was, it's not just me saying this, you might have heard of Eric Raymond, one of the founding fathers of open source, a real kind of big advocate of it. And he wrote a famous series of essays, and probably the most well known is the Cathedra on the Bazaar. But he wrote another one more on the economics of open source called the Magic Cauldron. And, you know, we don't have to read through all of this, but he sort of identified cases when open source, you know, doesn't work so well. I think one case study he used was John Carmack's inverse square root solution for efficiently running Doom on really kind of slow computers, etc. But interestingly, when you look at that, an example like that, it doesn't fulfill those three criteria that I just listed. I mean, the code will be relatively short, so that, you know, if it was open source, copyright protection, which open source licenses lean on, really wouldn't have any effect at all. You could just re-implement it. It was all about the idea. You know, these projects tend to be sort of kind of less modular things in computational science, as I'll go on to explain. So really, he was sort of musing on, you know, open source is great, it works for a lot of stuff, but it doesn't work for everything. And what could you do to sort of tweak the model hypothetically to get it to work for more stuff? And he came to the conclusion that, you know, one way to do it would be to pay people for their contributions to a software project. But that, in fact, is very hard. I mean, one thing is, you know, how do you pay people sort of international, across borders? You've got to pay some anonymous guy. You know, which maybe we could do now. This was written in 1999. They didn't have cryptocurrency then, so maybe you could do that now. But then, even if you do that, you don't really know how much to pay people for different contributions, like who prices them. And so he said, you know, you'd have to have kind of coined this phrase of a super being, you know, trusted super being. He would just decide, you know, kind of unilaterally who deserves how much payment for different contributions, and you know, those kind of super beings are sort of a bit thin on the ground, so it's a bit difficult to see how you would do this. But it's interesting you use those words. I mean, the first paragraph there hints strongly at cryptocurrency, you know, a kind of a payment system. And the second one is, you know, do you have a trusted super being? Well, actually, Bitcoin was a bit like a trusted super being in the sense that it substituted for a trusted intermediary, which you otherwise require for sort of, you know, transfers of electronic cash. So it's sort of hinting at something there. And we can next skip to the next slide. Yeah, I was just saying Bitcoin. Yes, we can skip to the next one. I just wanted to say that. Okay, so Bitcoin famously uses proof of work. And this is the original proof of work paper written in 1995. So again, well before Bitcoin. And what proof of work is, one way to construe it, and they construed it this way in the paper, is a pricing function. It says it actually at the bottom line there in the abstract. So proof of work basically is a way of determining how much you should pay somebody for a thing. And so we have a pricing function. We have a sort of, you know, something which takes the place of a centralized third party, and we have a need to price things, of course. So, you know, these are the kind of pieces of the puzzle that we fit together. So yeah, skip to the next slide. So computational science. So what the innovation game is really about computational science primarily. So this is one of the categories of thing which open source works less well for. And by computational science, we mean computational chemistry, physics, and biology. We don't mean computer science, which is really a branch of mathematics. So this will be computational natural science that we're focusing on here. So it's simulations and inversions primarily. You mostly hear about simulations, and one of the reasons is because inversions are quite hard. So that, you know, people talk less about things that they're less good at because they can't see that, you know, it's not so impressive when you put it on YouTube. But inversions are sort of really what science is all about. Anything like medical imaging is an inversion. You're taking a state at a later time, sort of scatter of some EM radiation, trying to infer what happened at an earlier time. And scientists generally want to do inversions. They want to take some sort of measure measured output and infer from that what were the sort of initial conditions which led to that measured output. So it's the simulation inversion is the difference between forwards and backwards in time. And because it's all essentially based on physics, this is natural science, as I said, second law of thermodynamics implies, and that means that inversions are hard to solve but easy to verify, which is a necessary property of proof of work. Okay, so we can skip to the next one. And, just as, this is written in February the 3rd, 2023, actually, so it seems quite topical. So if you're interested in why it is that, inversions are hard to perform but easy to verify, you could always read Stephen Wolfram's Computational Foundation of the Second Law of Thermodynamics. Like, if you're having trouble sleeping, I'd recommend that one. Skip to the next slide. ASICs is decentralized. So this is just to confirm that. So, why didn't people use things like, inversions, for example, in proof of work before? And the reason is that it was believed not to be possible. And this is Polstra's paper. I think he's at Blockstream, and he just talked about the reason why cryptocurrencies are secured by optimization-free, quote unquote, proof of work, is that if somebody finds an optimization for the proof of work sort of in the algorithm, he says, it's a strong motivation to keep it yourself. That's not, I would say, that's not the kind of the greatest reason. Because if you discover a better ASIC, for example, there's a motivation to keep it yourself. What the economics are that, with ASICs and things like that, you end up just it makes more sense to mass produce them and sell them. You make more money that way rather than just keeping it to yourself. There is an issue with the fact that if you find a sort of software or optimization, it's a little bit hard to sell than maybe just a piece of hardware. But anyway, it was going to be previously believed that you couldn't have optimizable proof of work where you could find a more efficient algorithm. Famously, they optimize the proof of work by finding more efficient pieces of hardware to run it on until now. Okay, so we'll skip on to the next one. And just, won't go into the technical details, but the way that we solve this problem, there's a sort of analogy. So imagine if you had we actually have lots of proofs of work for lots of different types of inversions in sort of diverse areas of computational science. And imagine that one of these sort of proofs of work was just like a guy in a boat, and he was sort of, he found an optimization, he suddenly became 100 times or 1,000 times stronger than everybody else. If you think about it, wouldn't really, it would make the boat faster, right? But there'd be a limited degree. He wouldn't just sort of blitz all the other boats completely, because he has to row in unison with the other rowers, right? So there's a limited amount of effect he can have on the whole boat, because the other rowers, in a sense, hold him back, constrain him. And this is the same if you use multiple proofs of work. And the only assumption is that you're not going to find large algorithmic optimizations in all of them at the same time. But if you do find it in sort of one or two, or even a small minority, the sort of degree to which the discoverer can benefit is constrained, and therefore the economics work out that it's just more, it makes more sense for them to enthusiastically share their optimization and get money from other people rather than try and keep it to themselves, because their benefit will be limited. Okay, we'll skip on to the next thing. So this is the flows in the innovation game. We start at number one, a benchmarker, which is what we call a miner, really. Benchmarkers are similar to miners in Bitcoin. They sort of pick their hardware, as Bitcoin miners would, but they can also pick the algorithm with which they get to solve a proof of work, which is a random instance of a scientific inversion. And if we go to number two, they get rewards from that, from doing the quote unquote benchmarking, which is just the same as mining. And each time they do some mining and they solve one of these problems, they're going to get a token reward themselves, but they're also going to give a part of that token reward is going to go to the innovator, so-called, who uploaded that algorithm. Obviously, they're incentivized to choose the best algorithms, and in fact, the algorithms which the benchmarkers select are the measure, in our system, or the sort of define which of the algorithms are the best at any given time, because of course the benchmarkers are rational to select the most efficient one. So the innovators also get a sort of cut every time a kind of a problem is solved using one of the algorithms they uploaded. And so you can see you're getting a sort of a market mechanism here. The benchmarkers really just want to mine most efficiently, and so there's a market mechanism selecting which sort of innovators and which algorithms are the best. And this is kind of interesting, especially if you imagine that some of these inversions could be quite esoteric things, early stage research, and maybe how do you keep a plasma in a toroidal fusion reactor stable or something like that. There really is no market for these things, maybe for another 20 years or 50 years. And so this is one of the issues with science, like because there's no market allocation, it's so uncertain that you get a sort of difficulty in science, sort of Matthew effect, and rather than the kind of having an objective market measure. But in this case, because we can select problems which are known to be important, but maybe at a very sort of early stage of research, and that they are valuable right now, at least to somebody, the benchmarkers. And what they are doing, even though just solving random instances, is they're providing an incentive to innovate and move that problem forward with more efficient algorithms. So we go on to number 5. These algorithms will embody a certain amount of IP, and the IP is captured by the innovation game, and it's available to be licensed by commercial enterprise. They're not all early stage problems and fundamental problems. They can be sort of late stage and stuff with current value as well. And number 6, the commercial enterprise will pay a subscription fee in return for this. And because the subscription fee is means tested, it's sort of, you're not excluded on the basis of the ability to pay. So the idea is that commercial enterprise, if it's not making any money, it doesn't have to pay anything in order to use all these things. And that's a bit like a tax. The government sort of tax, I suppose they tax profits. So you don't get people saying, oh, we can't pay our tax, because by definition, if you weren't earning any profit, you wouldn't have to pay any tax. So you can always pay, afford it, and that's the same here. So here on the right, we're just saying that problems are created. So we just put in problems which are known to be scientifically important. It is true that you might say, maybe there are some problems out there which are, they're important, but they're not known to be important yet, and they'll be discovered that they're important later on. I mean, that's absolutely true, but there are a lot of problems which are known to be very important, and people just work on them and trying to make them find more efficient solutions for them all the time. And these are the types of problems that we want to put in the innovation game. In particular, there's no option to pay to have your problem put in. These are going to be sort of the world's problems, rather than some individual guy's problem. So that we don't have that option. They're a created set. The problem instances are random. I just want to emphasize this. So this is not so-called useful proof of work. Useful proof of work, by the strict definition, is that the computations are solving sort of real life problems such that the output is valuable and interesting. In this case, it's not the case. They're random instances. So they're just not. It's unlikely they correspond to any real world thing, and that the whole thing is just an economic framework to attempt to the objective of which is to incentivize the optimization of routines for solving these problems more efficiently. Source code must be published. Everything's sort of out in the open. It's very much like open source in that sense. There's a possibility of a free rider problem because people could just take it, but for very interesting reasons, that open source tends to work quite well, especially for the successful problems, which we can go into. There's a build up of social norms, for example, because people are on board with the creation of a public good. So it leans on that, and so we know that can be successful. License fees create token demand, so license fees are payable in the token. Token means it can be decentralized. It sort of makes sense. This isn't, I wouldn't say that blockchain and decentralization are the sort of raison d'etre of this whole scheme. It's not sort of, central decentralization for the sake of it. I would say that, it's decentralization because it would be inappropriate for it to be centralized. Like if this spins up and it becomes big and very successful, you don't want to say one company having any control over the world's science IP, or at least computational science. And whose currency would you pay it in anyway? Would it be like the petrodollar, where everything's pay for in oil? That would be kind of inappropriate as well. So it's sort of like a neutral method of payment, and it's sort of a structure which doesn't belong to anybody. And you incentivize 3 types of optimization. So I talked a lot about algorithm optimization, but code optimizations can make a huge difference, be very valuable. Those are also incentivized. Those are also remunerated. And hardware optimizations are incentivized by the fact that there's a large market created by the benchmarkers for hardware on which they can benchmark more efficiently, so earn more tokens. Skip to the next one. How does STIG accelerate science? So I said the side of is accelerating science for computer economics. So it accelerates science in a slightly different way depending on what type of science you're talking about. I mean, this is all computational science, which pertains to other science too. In fact, it's not like biology is a subset of science. In that sense, computational science is part of all science these days. Chemistry, physics, and biology. It feeds into better theory. It feeds into better experiment, and experiment and theory feed into better computational science. So there's sort of a triad between them. But more specifically, in terms of the innovation game, commercial research can be privately funded, but performed on an open and collaborative basis. By commercial research here, that might not be the best term. I didn't mean research necessarily just conducted in a commercial context, like at Pfizer or something. I mean like commercially viable research. So in academic research, universities these days, they do research where they're sort of paid by some kind of outside party. It's quite common. And the deal is, we'll give you money for your research, but if you produce some IP, we own that IP, right? So that's a proprietary sort of deal for them. And academic researchers, they do kind of take that deal because then they get to do the research which they love. But in this case, the deal could be, I as a private investor will give you some money, you do the research, and if there's good IP that comes out of it and you earn tokens in the innovation game, I get to own the tokens. That is the deal. And the IP goes into the innovation game and it becomes a public good. So it's a different model on which commercially viable research can be performed, which means that it's open and collaborative rather than proprietary. And that leads to efficiencies, better research, and that sort of thing. Early stage and fundamental research can achieve higher participation. So as I said before, open and collaborative is the best thing, but it only works if you have decent levels of participation and a lot of fundamental early stage research, even though it can be open source because it's funded by the government, and the government often encouraged open sourcing. You don't get many participants, and that's because the incentive isn't high enough. And the third one, accelerating generation of non-proprietary scientific knowledge. It just happens because of the first two. So you get more, you sort of, accelerate the topping up of the stock of non-proprietary knowledge. Okay, skip to the next one. That might be the last slide. Yeah, okay, this is just contact. And so that's it. How'd I do on time?
Fantastic. You nailed it, John. And
Right.
I love this theme. We had some folks from the Berkeley Boink project on a few months ago. We had some groups, Petals Machine Learning, which is doing volunteer-based machine learning. But I love the thread of it's good application of crypto, it's good for science, and then people also can have an economic benefit. You can sort of serve all the outcomes.
Well, that's the thing. I mean,
ideally.
the dream, of course, is making that which is good. We actually, because it's not hard to know what is good, right? More fundamental science. When science is done, people share it and they make make all the source code available, and they make it sort of a public good. That is good. But the question is that profitable? Can it be done on a sustainable basis? And to me, the great dream of crypto would be to make that such that it is the case, because we designed the system that way.
I love it. All right, I'm going to give everybody else an opportunity. If anyone on the call has any questions. Oh, here's a question. Maybe touch on how huge algorithmic improvements can be.
Oh, that's probably from Ying.
Yeah. Or maybe that was a comment, but maybe we did cover that. Is there anything else that should be said about algorithmic improvements?
So that was that it is important. But so one of the reasons why algorithmic improvements, they sort of, as they said in that optimization free, that were kind of prohibited up until now, is because they can be absolutely gigantic. So the funny thing about algorithmic improvements they have, I mean, I don't know if you know anything about computational complexity, and there's various algorithms that have gone from, say, an n squared complexity to an n log n, which is almost like linear. So depending on what n is, I mean, n could be 100, but if n is 1,000,000, then that means it's 1,000,000 times faster, which is just absurd, right? So if you had a big mining network and somebody found a way, to make it 1,000,000 times more efficient, they would simply bankrupt everybody else immediately, and all the mining was centralized to them, which would be clearly unacceptable. So this is one of the reasons. Algorithmic improvements all types of improvements are very important, over time. But there's just the potential for more clever mathematics in terms of the strategy of solving things to make things sort of, absurdly more efficient. 1,000,000 times more efficient overnight because someone had a good idea in the shower, sort of thing. So it's they don't really top out, basically.
I love it. Very good. Well, this is a lot of material. I'm going to go ahead and hit pause on this recording for now. Get us posted up YouTube. John, thank you so much for presenting today. This is incredible content. Pleasure. And such a great fit for the things the community is interested in.
Great. Thank you, Wes.
All right.
Yeah, I was happy that we were able to to fix the issues to get the presentation. Very good. Thanks for that.
Yeah, I'm glad we did. Thanks a lot for your assistance.
Well
was
done.
awesome.
It takes a community, it takes a village, as they say.
It's true. It's true.
Yeah.
All right, very good. Well, we'll keep it going on the Slack channel. I'll post this out so everyone has access. And thank you so much for everyone for joining today.
Pleasure.
Thanks, everyone.
Take care.
Thanks, guys.
See ya.